Okay, so let's get started. So given this equation right here, find the derivative of both sides with respect to x. So notice that we have x, y, and r, but you're going to take the derivative with respect to x. Okay, so if you're doing a derivative that's not x, then you take it implicitly. So that's the new rule, but it's basically the same thing. Everything will be very similar. Same power rules, products, chains, all that stuff is the same. We just add this extra piece. That's all you got to do. Okay, so this time this notation will be best. So d dx of both sides. Got my r. So basically, you got to do the derivative of x squared with respect to x. So since these match, then you'll just do it like you've always done it. When they don't match, they have a different rule. Okay. So same stuff. Do your power rule, bring down your 2, subtract 1, right? This would become 2x. See how nothing has changed, right? With that first term. Do the same thing here. Bring down the 2, subtract 1, but then you have to multiply by dy dx. So it's kind of think of it as a chain rule. So you do everything the same, but tack on dy dx. So whenever it doesn't match up, simply put this piece there. See how this one doesn't match either, right? So what do you think this one's going to be?
2r times dy dx.
It's close. dr dx. So see how it's all the same? Just tack on the piece. So this is y, so dy dx. R dr dx. This comes from the chain rule, and if you saw the videos, there's a theory behind it. It's basically an implicit chain rule. Okay. But the way I want you to think about it basically is if they don't match up, tack on this piece. Okay. This is the implicit part. Once that's done, then you can solve for whatever they're asking. Okay. So right now they didn't ask for anything except take the derivative of with respect to x. That's all they said. So this will be, and we're done, right? Because they didn't ask us to do anything else. I just wanted you to see the implicit part happening. Okay. So if they say if it would have been y with respect to y, then you would have dx dy everywhere, right? And then this would have been normal, and then these two would have been implicit. Ouch. Are there any questions on this first example? So before we start doing anything crazy, I want to do a basic problem. I need you to see what's happening. Let me know if it makes no sense. Okay. So let me know. All right. I'm gonna turn the page. You guys cool with this example? All right, so let's do one from the homework. So they're gonna assume that you know how to do derivatives, and then you're gonna add that implicit piece. Find dy dx by implicit differentiation of 3x squared minus 3y squared equal to 4. So this time you're going to do what we just did earlier, but you're actually going to solve for this piece. You're going to isolate dy dx. Okay. So do the same nonsense. So first step is take the derivative with respect to x on both sides. So d dx eventually is going to end up being every single term. So if you skip this step, it's cool. Here we go. Do each piece, show your steps. So all I do is apply the ddx on each part. Derivative of constant respect to any variable will always be 0, doesn't matter. So this will become 6x, right? Bring down the 2. This guy will become 6x as well, but times dy dx. So the derivative part is done. So second step, isolate dy dx, because that's what they want. So first step, that should be a y, my bad. I'm going to move over this guy just because it makes me happy. No negatives. So I move this term. I did 6y dy dx on both sides. Divide both sides by 6y, and you're done. Just about anyway. These are gone. The sixes are gone. That means that dy dx is equal to x over y. So do y'all see is there any question on any of these steps here? The algebra or the derivative step or the new implicit rule?
I have a quick question.
Mhm.
So in the second step, um, when the zero just disappeared, it's because it's zero, right? Like it's just gone. You don't need to do anything with it.
Like where did the 0 go or why is it 0?
Both, yeah. I'm asking both things, yeah.
Oh, okay. So the zero came from up here, step one, right? Derivative of any constant is going to be zero. Now, after we finish our derivatives, we want to isolate dy dx. So basically solve for this, right?
Mhm.
In order to solve for it, I'm going to add this on both sides. So basically I moved this term over here, right? So I did plus 6y, right? Plus 6y. You know what I mean?
Oh, okay. And that's why. Oh, okay. So you just moved it. That's all you did. Okay.
Yeah, I think of it as just moving it over, but basically I'm doing this algebraic step here.
Oh, okay. All right. Sorry about that. I didn't see it.
No, I understand. So once you do that, again, we're trying to solve for this. So divide by 6y. 6y is gone. Sixes are gone. So this is equal to x over y, which is right there. So this is what they want. So most of the questions, you're going to take a derivative implicitly with respect to x or y or whatever the hell they say, and then you're going to solve for it.
So in the homework, if we just end up with x over y, we just put that in and that's it.
Yeah, that's the answer.
Okay.
Sir, the 16, that's a constant, right? So that's the 0.
Mine was a 4.
Or 4 on mine, it's 16. That's why, because the first one's kind of similar. So
Mhm.
it kind of helped me go through it.
Yeah, that'll be the same steps. So remember, derivative of any constant will always be 0.
Mm-hmm.
So that's why this is gone. So if it's 16 or 2000, doesn't matter. It's going to be 0.
Okay, just making sure. Thank you.
Okay. So the rest of the homework will keep repeating itself. It'll just get the derivatives will get harder and harder, and the algebra will get messier and messier. But we're going to keep doing examples. Just want you to know that in essence, this is what they want over and over again. Okay. Any other questions on number one? Okay. Let me know. So find dy dx by implicit differentiation. All right. So since it says dx at the bottom, that's the hint. Do d dx of every single term. If the x's don't match, then do it implicitly. Okay. So I'm gonna skip that first step. This basically gonna do or be d dx of every single term, every single one. But notice we have x squared times y squared times x. So this is a product rule, right? Both of them. So this is basically going to be derivative of the first one times the y plus the derivative of the second part times the first part, 5x squared. So that's this first one. Then another product rule. Oops, made a mistake there. First part. No, that's fine. Derivative of this guy, first part, times the second plus derivative of the last part times this. Okay. Before I go any further, do you see where all this came from? We have two product rules happening. So we set up the product rules, but you have to do it implicitly. Right? Instead of using f prime g prime, I used derivative of the first part times the second, derivative of the second part times the first. So this would be 10xy plus, what's the derivative of y?
dy dx.
Yeah, so this will be 1 times the dy dx. But yeah, essentially you end up with just this right here, right? Then again, derivative of 4y squared, what is this going to be?
8 dy dx.
8y dy dx. And then that x is still hanging out. Derivative of x. Just the 1, right? So all the derivatives are gone. So this first step is doing your derivative implicitly. Any questions on the derivatives? There was a product rule and power rules.
How do you get the 10 and the 8 in this part of it?
And okay, so derivative of 5x squared, this one, you have to bring the 2 down, right? So 2 times 5 is 10, and then you subtract the 1. Do you remember the power rule?
Well-
What's that? You need to see another step right here. Is this okay? All right, I'm assuming you're good then. So the 8 will be 2 times 4, which is 8, and then you subtract 1 from the power. That's where this came from. This just came down for the ride. Derivative of this is a 1. This comes down.
I have a question.
Mhm.
So Okay, so the d over dx, are you just adding that before every single can you even write on here? Crap, okay. Okay. Never mind. I can't even show you. I don't even know what I'm talking about. The d over dx, is it before every single little part of the equation? Is that all it is?
Yeah, I mean, think of it as like before, remember we would put like a quote, meaning take the derivative, right?
Yeah.
So it's the same thing. It's just now we're using this instead of a quote or a prime because you
Hmm.
need to know with respect to which variable. That's when we start caring about this. So uh, instead of having this on each one, right? I'm doing d dx. So yeah.
Instead.
Mhm. So essentially,
Oh,
they want you to do the derivative of every single term, so every single piece. There's
so
three.
I'm sorry, keep going.
No, that's fine.
I was gonna say, okay, so what if it keeps getting smaller and smaller and smaller? So then I keep adding it and adding it and adding it behind every single one?
Well, you do it for every term. So remember, a
Every
term is something that is separated by a plus, right? So you have one term and two terms, and then you have another one over here on the other side.
uh-huh. It's because I
So,
see you separated the on the third line, you separated, I guess, the y from the 5x squared. Why did you do that?
so from here to here, so here I'm setting it up, right? I'm about to take the derivative.
Uh-huh.
Here, the derivative is beginning to happen because I needed, but it looks like this because of the what's it called, the product rule. So let me find the note real quick. So remember, if you have like, for example, two pieces like e to the x times x cubed, and you do the derivative of the entire thing, right? Then you would get, sorry, you would have to do the derivative of the first part. So instead of using prime, we're going to use the d dx. So let's scratch that. Ignore this quote here. Sorry, it's going to bother me. So pretend we're doing the primes, but we're not because it's the same. We're doing d dx of your function, d dx of the single term. But the rule, the Potter rule says you have to do the derivative of the first part times the second part plus the derivative of the second part times the first part.
I'm gonna take a screenshot of that. Hold on. I mean a picture. Hold on.
Yeah. So this is from 3.3, I believe. Maybe 3.4. This is 3.5. You remember? Does this make sense?
Mm-hmm.
Yeah. Adam Dobbins just posted the general rule. It's also in the thing I sent y'all, the formula sheet.
Mm-hmm.
So if you have two pieces and you do it over the entire thing, it has to be done as a product, using the product rule. So there's going to be a plus in the middle.
Oh, okay. All right. Thank you so much for that clarification. I apologize for that.
Oh, that's okay. I mean, it looks really weird, right? It looks messy, but it's because we have x squared times y. These are two different parts. So you have to do the product rule on both parts here. That's what's happening right there. This is coming from, this is the first one, right? And this is the second part right there. Then you do it again for these two. This is a product rule for these two products there, y squared and x. That makes sense?
What about that y, that singular y after 5x squared? Did that come from the first that term in top two or?
It came from this one. So derivative of y is here. So
Mhm.
the derivative of the second part times the first part. The derivative of the first part times the second part. So this is my f prime g plus g prime f.
Okay. Okay.
Is the notation throwing you off a bit?
Yeah. Yeah, it kind of is, but it's okay. It's okay. I just gotta keep practicing and then I'll get it. But thank you. I see it now.
You see it? Okay, good. Yeah, as long as you see it, it's just we're shifting because the homework uses the f primes and g primes all the time, but eventually they start shifting to this because we have no choice. We have too many variables. So if I put a prime, I'm like, well, prime, what does that mean with respect to which variable? So it has to be clear. That way you know where to put the dy dx or the dr dx.
Thank you.
Mhm. Okay. So here all the derivatives are done on the fourth line. Just solve for dy dx. So I'm going to keep these on the left side of the equation. I'm going to subtract these two over here, leaving me with this. All I did was subtract 10xy on both sides and subtract 4y squared on both sides. So I'm solving for dy dx. You need to get all of those on one side. So factor dy dx, leaving you with 5x squared plus 8xy or whatever, doesn't matter. Divide this garbage out and we're done. So this is gone. So dy dx is what they wanted. It'll be equal to this. 10xy minus 4y squared over 5x squared plus 8xy. So any steps? Let's go to the next one then.
I have a question.
Mhm.
So the dy dx, that is the derivative y in terms of the derivative of x? Or how did you word that?
Yeah, pretty much. The wording in the book is yeah, derivative y with respect to x.
With respect to x. Okay. And so does this mean that the derivative of y is that numerator there?
Um, does numerator here?
Yeah. Since it looks like a fraction on this side and it's a fraction on this side, is the derivative of y that numerator and the derivative of just x the denominator?
No, not necessarily. We could solve for dy, but it would have the dx component would be over here.
Oh, okay, I got you. Yeah, that makes sense.
So then that would be called I think if you, in the next I think it's towards the end of chapter 3. They
I'm
talk
getting ahead of
about differentials. That's a little different.
Gotcha.
No, 1 second, guys. Okay. Let's do number 4 from the homework.
¿Me veo bien? La rompiste el Bizarrap Session ahí,
Leandro, your mic.
modo casa zombie ahí.
Find dy dx given square root of xy equal to x cubed y plus 14. So this one, you can tell is going to be a little difficult here because you're going to have to do a chain rule, and during the chain, you're going to have a product, and then that product has to be done implicitly. So as you can see, the derivatives are getting harder and harder. Then the algebra will just be messy. Excuse me. So I'll write the steps this time. Okay, so do d dx of each side. Right. So first step, change this to a power. We're going to do this d dx on each term. So this one becomes uh, so do your power rule first. Right, remember the chain rule says leave the inside alone, work on the outside. 1/2 minus 1 times the derivative of the inside. So this part will be, this will become the implicit part. Now here we have a product rule. So you'll do d dx of x cubed times y plus d dx times y of x cubed plus 0. Before I go any further, do y'all see the the derivative rules? Excuse me. This section is assuming you've mastered the power rule, product, quotient, and chain rules. And they're adding this new rule um, combined with all those. Okay.
I have a question.
Mhm.
Where did that 1/2 come from?
So we can always change a root. So if it's root 2, then you can do 1/2. If it's cube root,
Oh,
do 1/3. Once you change it to a power, then you can do a power rule. Excuse me.
thank you.
All right. You guys are cool with the chain right here and the product here. So this inner chain creates another product, which sucks. So derivative of the first one times the second plus derivative of the second part times the first part, put brackets. That's this derivative here. And let's go ahead and start doing the derivative on this one. Derivative of x cubed. No implicit part because it's an x. Derivative of y will be 1 times dy dx. So you end up with x cubed dy dx. Derivative of x is a 1 times y. Derivative of y is 1 times dy dx times the x. Okay. All the derivatives are done at this point. Any questions on the product rules? Okay. So I still need to solve for dy dx. This is garbage. How can I make this prettier? Do you agree if I multiply both sides by 2, this half will be gone? It's not necessary. It just looks ugly already. Is there a nicer way to do this? No. I'll just distribute. I don't want to confuse anybody. So multiply this on both of them. We'll get y over 2xy to the 1/2. Since it's negative, I'm just going to go ahead and put it on the bottom. So this times this times this. You guys cool with that? I skipped one step there.
Which step did you skip?
I moved this negative exponent to the bottom and then multiplied it on both of them. That's why it's down here.
Oh, okay.
And then the half times both, you'll have the 2 down there as well. Just so it looks a little better, you know. But it still looks horrible. So I'm going to get these two on one side and these two on the other side. Because I need to solve for dy dx, right? That was the whole goal. I put that as step 2. Dang it. Oh well. Step 2 solve for dy dx. That's what we're doing now. So this will be over here. This guy will be moved over here. This will be moved over there. Factor dy dx. We'll be left with x over 2. So let's change it to square root because I'm tired of writing it. Okay. Okay. So all we're doing is algebra. All this. So divide this down here, and we'll have dy dx. Pretty much done. It's kind of nasty though. Because I'm out of room, I'm gonna skip this step here. So divide this on both sides. You'll end up with right? Yeah, cool with all the algebra so far. Any steps that are strange? Because it's a little heavy on algebra. Okay.
So the whole fraction, that's just the answer, right?
It is. I mean, we solved what they wanted, but it's a complex fraction.
Mm-hmm.
So technically, we could do one more step to make it not complex. But yeah, technically, if you got this far, it's good enough for me, you know. But I'll show you the next step. So in order to cancel all the fractions, you would multiply the entire top by this, the entire bottom by this. So this will cancel here, and then this will be tacked on here. This will be tacked onto this, and then this will be canceling this part. So the prettiest I can do is this. Oops. Technically, I can multiply the 2 and the 3, but I'm gonna leave it there because I'm out of space. But you see what we're doing, right? Or no? That you see how the idea is the same over and over again. It's just do the derivative that they request. If they have dy dx, then you're going to do d dx. If they say dx dy, then you're going to do d dy. If they wanted dy dr, then you would do d dr of every single term. Then once you've done that, once you finish all your derivatives, you will solve for the specific thing they're asking about.
I have a question.
Mhm.
Um, for the square root of xy there, could we turn that into x to the 1/2 and then y to the 1/2 and then combine that with the x and the y and next to the 3 over there?
Yeah, you could. No, you technically could do that.
Okay.
You would just have uh, fractional powers and so on.
Hmm.
Nothing wrong with that. I think that might be a little prettier. But as long as you don't have a complex fraction, it should take it. The homework. But on an exam, I mean, I haven't graded the last test, but you'll see that, I mean, as long as you're showing your steps, if things get really messy at some point or you get lost, I mean, I'm gonna give you as much as I can, if not most of it. If you demonstrated, you knew what you were doing, but the algebra just got disgusting. You know what I mean? I mean, you should know your algebra, but I believe that's the hardest part of this class is remembering it all. Okay. Seven. Second. All right. You have any questions from the homework that you're struggling with? Y'all doing okay? I extended everything so far from chapter 3, I think. I'm assuming you're all just pros and it's no big deal.
No, I had trouble on a question. I'm just trying to find it because I had
Okay.
written it down for whenever, like after class or whatever, but I need to find it now. Hold on.
Yeah, take your time. Because I want to start a new section, but I'd rather you process this first. Because we're still a little ahead.
Which section is this?
This one is 3.5.
Oh,
I have a question.
Mhm.
Some of these problems take a lot of work to figure out, and I just want to know if there's any tricks or shortcuts to figuring out if by the time we get to the answer, if it's a possible right answer, or what we can do to like kind of confirm that as we're, when we're taking the test, like, is this the right answer? Is it just plugging it into my calculator or?
Um, you mean like in 3.5 or do you mean in general for chapter 3 or?
Yeah, I mean, just in general, because, like at any point during all this work, I could have accidentally screwed up a sign or skipped a variable or something. And, you know, I just want to be sure, like during the test, like what's the best way to make sure, like by the time I get to an answer, I know for sure this is the right answer.
Well, I'm not gonna, I mean, I should, but I'm not going to take points away if you make small errors like that. If
Hmm.
you're showing your work and you just miss them small or you multiply wrong or you do something weird, that's not gonna be a big deal. If you're demonstrating you understand the product rule, the chain rule, power rule, and you're not having problems, then that's kind of what I want to see.
Okay.
Um, so on an exam, it's not gonna be like the homework. Homework will be a little harder because you have plenty of time, right? And that's you have plenty of time to get it perfect. On a test, you don't. So I'm gonna try to give you something not like this because this would be uncool on a test, I think. Um, but if it was there, if I saw you get to here or or there, like this part, yeah, I'd give you most of the points, if not all of it. That's pretty good. Even if there's a sign error here or there, doesn't matter because you have if you got to here, you have shown, right, that you can do the implicit derivative and you understand that there's products and chain rules happening. That's great at that point. Does that make sense?
Yeah, because a lot of the times during the homework, I found that I just kind of kept going with simplifying, and then somewhere along my simplification process, I screwed up and got the answer wrong, whereas I may have gotten it right halfway down. Does that make sense?
Oh, like you make a weird error in the middle and then the rest is
Yeah, like I
garbage.
had the answer right, and then but it was ugly, and I wanted to simplify it a little bit, so I started simplifying it, and then screwed something up in the simplification process, and then I got the answer
Oh,
wrong.
yeah,
Yeah.
that is frustrating. That happens. I mean, I think that's just that mastery of algebra just comes with time, the
Mm.
polishing. But it happens to the best of us. What pisses me off is I'm doing like a 3-page question and I messed up on line 3, so the rest is just nonsense.
Mm.
That's really frustrating. But it happens, man. And the homework, that's the time to, you know, put a lot of time in. Oh, see, someone requested this guy. The sine pi x plus cosine pi y cubed equal to 24. So the derivative of both sides is going to be another chain, but with trig functions. All right. So this is a chain rule. So the outside derivative would you bring down the 3. Don't mess with the inside. Subtract 1 in the power times the derivative of the inside part. Don't put brackets right here. So distribute this ddx on every single term. Just so it doesn't look too weird. Oops. 2. So what is the derivative of sine?
Cosine.
Cosine. Then it has that chain piece, right?
Yep.
It'll be pi cosine pi x plus this will become negative sine pi sine pi y dy dx. So there's the derivative. So we're going to isolate this dy dx. That's what they want. You can go about that many different ways. I'm going to do the way that I think is the easiest to understand. So distribute this on both of these. So it'll be 3 pi times cosine pi x minus 3 pi times sine pi y dy dx. Oops. Dang it. That distracted. This times this. Negative 3 pi. There we go. All right. So I'm going to move this guy to the right-hand side. Divide all this garbage to the left. Leaving me with this. You'll have 3 pi sine pi x plus cosine pi y times cosine pi x over 3 pi times the same nonsense times sine pi y So this will be gone. dy dx will equal should be right. Anyway, does that make sense?
I have a question.
Mm-hmm.
Can cosine pi x over sine pi y be simplified into a cotangent or no?
No, because they're different variables.
That's a shame.
Tempting though, right?
Yeah.
I think I wanted to, but no. You don't have any other problems you want to work on? Okay. Let me take roll then.